Welcome to Chapter 11 of the Shapley Values series. In this chapter, we will have a look at Monte Carlo sampling and how this method helps us in calculating Shapley sampling values with reasonable efforts. Let's dive right in. So, creating predictions for every possible subset and for all possible feature values is likely too cumbersome to calculate Shapley values in reality. To once more get us out of this pickle, it's time to finally put the sampling into Shapley sampling values. Instead of iterating through all possible subsets of S, and then having to calculate the predictions for all possible feature values, we will approximate Shapley values by leveraging a common statistical technique called Monte Carlo sampling. The main idea here is to repeatedly draw random sample values to arrive at a solution in a much faster and more efficient way, while that solution should still be really close to the exact Shapley values that we would obtain via the exact calculation. To see what this entails, we will follow a recipe for a Monte Carlo sampling approximation and apply it to our model example. Let's say we want to use this sample from our previous example of a model containing 4 features. This corresponds to step 1 in the recipe, defining a sample of interest x. Next, we define the feature of interest j for which we want to calculate the Shapley sampling value. Let feature j be temperature. That means we want to understand the effect of the temperature of 20 degrees Celsius on the prediction for the sample of interest x. Next, we draw another random sample z from the dataset. Let this be the random sample z from our dataset, which comes with different feature values for inventory, temperature, and so on. Next, we will reorder the feature values for our sample of interest x and the random sample z. For our sample of interest, inventory is now the first in order, and temperature is second in order. Note that the order of features is not actually changed. Each feature remains at the same position when passed to the model. We are simply changing the order as a visual trick, which we will use in a later step of the approximation recipe. Then we also apply the same new order to the random sample z. Next, we construct two new samples, x sub plus j and x sub negative j. First, let's look at what sample x sub plus j entails. It's denoted as plus j because all feature values that are placed after the feature of interest j in our list of feature values will be replaced by the feature values from our random sample z. All the feature values up to and including feature j, in this case temperature, will stay the same as they are in the sample of interest x. Next, let's look at sample x sub negative j, where now all feature values, including the one for feature j, are replaced by the values from the random sample z, and only the feature values that are placed before feature j in our list are filled from the sample of interest x. Now we have created two samples that are different from the original sample, but still contain values that are realistic feature values from the underlying data. This step approximately accomplishes what we would do if we solved the Shapley values computationally, which means using the whole distribution of possible feature values to understand the impact of a missing feature. However, in this approach, we sample only a few data points from these feature values' full distributions. In the sixth step of our recipe, we calculate the marginal contribution from these two samples. To calculate this marginal contribution, we first use our machine learning model to create a forecast for the sample x sub plus j. Then we use the model to create a forecast for the sample x sub negative j. And finally calculate the marginal contribution as the difference between the two. This marginal contribution expresses how the prediction changes for a different value of feature j, here temperature, for two given samples. Only looking at two data examples is not enough though, which is why we repeat steps 3 through 6 m times, where m is a very big number. That means we will continue drawing many random samples, reorder them randomly where the order can be different within iterations of m, then create our artificial samples, and calculate the marginal contribution. Notice how coming up with different orders of features and consequently replacing a different number of feature values approximates the summation of different subsets S with different size. Lastly, the Shapley sampling value for the feature J is then calculated as the average of all these marginal contributions over the m iterations. This value now corresponds to the Shapley value for the temperature of 20 degrees Celsius for this prediction, that is, the effect of this specific temperature on this specific prediction. We have now successfully calculated the effect of a specific feature value on a given prediction by calculating its Shapley sampling value in an efficient manner by leveraging Monte Carlo sampling. Congrats!